Hi, this is Mrs. Gorley, and this is the 10.2 lesson in BC Calculus on polar graphs. And then we'll also get into derivatives of some polar functions too. So this is kind of like parametric, where this was something that used to be taught in pre-calculus, and so we didn't have to go over it quite as in detail before. But we're going to have to do the pre-calculus stuff here before we can get into the calculus part. Has anybody in here ever dealt with polar coordinates before? Well, it's kind of like, think about yourself standing on the North Pole, just met Santa, and now you are, you're looking at direction. So think about a globe. You know how we have longitude and latitude on the globe? All of those lines that are coming off of the pole are all a degree on a unit circle, because the Earth is a sphere. So if you're standing at the pole, you basically have a unit circle that you're looking at for all of those angles. So it's kind of, that's where we get this polar, the idea of a polar is there's a pole in the middle, and then you're doing all of the angles out from that pole. So it's a little bit different looking than our XY coordinate plane, which we call our rectangular form. This is more circular on it. So first of all, how do you even say like a point or anything in polar? Well, it's based on a direction from the pole and then an angle from the pole. So instead of saying let's go over whatever x value and up y value like we do on here on a rectangular coordinate plane, we're going to start it at the origin, at the pole, and we just say a directed distance is our r, and the angle is theta. You would think that you would want to say like the theta is like your x coordinate, like you do theta and then r, but it's actually r and then theta. Okay, so when you list a point, you list how far you're going to go from the pole, and the angle that you went is actually listed second. It seems backwards to me because most of the time you would want to know your direction first, but anyway, that's just how it is. Okay, and then the polar axis is just like, it starts like the positive x-axis, and that's your polar axis is the same thing here. That's like on your unit circle where you start all of your angles from, is that positive x-axis part there. Okay, so that's how you do a polar coordinate. So you notice that it's convenient then to make instead of our grid for a rectangular, we're going to make circles. We're going to have concentric circles on here and then they're going to be intersected by radial lines right through the pole. So radial lines are just lines that go through the pole. Okay, so here's like a typical blank polar graph here, and we're supposed to first plot these points on there. So this is your problem number 1. So you want to go to 3, so go out to 3 on the circles, the third circle there, the circle with radius of 3, and go over to pi 6, which is our first line here, and graph your point there. So you got to know your unit circle basically, so you know your radians in the unit circle. Don't necessarily need to know the points of the unit circle, but you do have to know, where is pi halves, where is pi, and that kind of thing, Okay, so this is actually cut. Which angle on the unit circle is not represented on these lines here?
The pi fourths.
Yeah, pi fourths, because here's pi halves, right? Here's 0, here's pi, here's 3 pi halves, and then it goes back around to 2 pi and keeps going. And so you've got going up pi sixth, and then 2 pi sixths, which is pi thirds. So the pi fourths one would be right there, right in the middle there. It's just not on the picture here, but it's still there. I mean, you could graph something at that if you want. Okay, so let's graph all of our points. Take all of those points on problem 1, and put them on there. So we have our 3 and pi sixth. We have 4 and pi. And we have 3 and negative 5 pi 6, so we're going the other direction. So right here, actually I could just label these A, B, C, and D. I guess I don't have to, because they are already labeled over here in our problem. So A, B, C, and then Okay, D is a little tricky because you're supposed to go to -2. So what happens is each one of these, this is why I actually think of the angle first. You go to the angle. So if I go to 3 pi halves, I'm actually facing this direction like that. But if they tell you a negative radius, then pretend like you're facing in this direction and you go backwards too. So you're actually up here at D. Okay, so instead of going out in the same direction, you go the opposites. So that could have been said, instead of the way that they said part D here, they could have said, oh, that was +2 and pi halves. It's the same way to get to that point. So unlike a rectangular coordinate plane, you can say points on a polar coordinate plane an infinite number of ways. You know, we could do it like we did these two here, where you use a positive or a negative radius. You could go around the circle again, you know, and say 5 pi halves kind of thing instead of pi halves. I mean, there's an infinite number of ways to say a point on a polar coordinate, just like we can go around the circle forever. So
how does this work since the Earth is flat?
yeah, you'll have to talk to the flat earthers about that. Okay, so with rectangular coordinates, each point has a unique representation, but like we said, we can have lots of different representations of the same point here. So for number 2, we're supposed to write the rectangular point in polar form, and so this is one point that we're going to write in a bunch of different ways. Okay, so we have A, B, C, and D. We're going to write it in all these different ways. So first of all, how would we convert this point here that's in rectangular form into polar form? What would you do? What do you think? Any ideas? Well, we got a graph there. How about we graph it first? That might be helpful. So let's go over -1 and up square root of 3, which is about 1 point, I don't know, what is it, about 1.6 or 7, something like that. So it is, here's my point. So just like on the unit circle, if we drew a right triangle on here, all the little lines on the unit circle, remember, come from right triangles. If we draw a right triangle there, then we can say the sides of this triangle are 1 down here and square root of 3. And I'm going to say this, even though that's a length of a side, I'm going to say it's -1 down there, just so I remember that that was my direction, was left. Like that. Okay, so could you come up with then what this distance here is? How would we find that? Pythagorean theorem, yeah. 1 squared plus square root of 3 squared is equal to, we'll call it r, since it's a radius of a circle, squared. So what is that? 2? Is that right? R equals 2. Okay, we just found the radial distance there. Okay, we found our first coordinate then is 2. The r is 2. So how do we find this angle here? What do you think? Trig, exactly. You have these two sides were given to you. Well, that's the opposite and the adjacent of this angle. If I put a theta right there, theta is actually out here. We'll call this theta prime or theta sub 1 inside there. Theta is actually the angle that you've rotated. So this is just our reference angle inside here, inside the triangle. So we could say, to get that reference triangle, or that reference angle, we could say that is, that angle, the tangent of that angle is equal to the opposite over the adjacent. Okay.
Easier to just do sine with.
You could, but I did tangent for a reason. You'll see it coming up later. You could do sine, you could do all sorts. So where is it that the tangent is square root of 3 over 2? Or like Snare was saying, you could do the sine was square root of 3 over 2, or the cosine was -1/2. What point is that on the unit circle?
2 pi thirds.
Yeah, 2 pi thirds. So you got to know your angles. So it's actually, this is this reference angle right there. The reference angle is pi thirds. So our actual theta, probably don't want the little thing on there, little sub 1. Theta is actually 2 pi thirds. Okay, so we know that this angle is 2 pi thirds. We know that our radius there is 2, our directed distance. So we can write this point as 2 and comma 2 pi thirds. This one says to give a radius that's positive and give an angle that's positive. So we've done that. So the next part says give the radius positive again, so we'll still say 2, but this time they want an angle that's negative. So can you give me an angle that's negative that is coterminal to that 2 pi thirds? Lands in the same spot. What angle going the other direction, like this way? What would that be? Right, negative 4 pi thirds. Okay, you got to know, this is where knowing your trig is, and those radial lines or radial angles are really important. Okay, next time the next one says, excuse me, make the r negative. So this time I'm going to go negative 2. Okay, you can still take a 2 because it's obviously that distance. And they want a positive angle. So you got to think you want to end up right here still, but you've got to go backwards to get there. So you actually want to be facing out this direction, and then you can move backwards 2 here, a negative 2 that way. So what's that angle here going in this direction? First of all, it says they want theta positive, so we want actually this angle going around. What would that angle be? Come on, guys, think. Fourth quadrant.
5 pi over 6.
Yeah, 5 pi 6, 5 pi thirds, yeah. Because up here, if this is 2 pi thirds, then in this quadrant down here, you've added pi to it. You're at 5 pi thirds. Okay, you just add pi to it to get down to the one that's directly opposite of that, because pi is the same as 180 degrees. So this is 5 pi thirds. Okay, then last one says to write r as negative, so we'll put negative 2, and this time they want an angle that is less than 0 or negative, so now we want this other angle going this direction. There, what's that angle right there going backwards instead of forwards? Negative pi thirds, yeah. Okay, those are all representations of the exact same point. They all end us right here at this point. Okay? So the thing that gets people mixed up is that negative radius. You just got to think, I'm going to face the direction of the angle, but then I'm walking backwards. So I'm going actually the exact opposite direction of that angle. Okay? Now, again, we could just add 2 pi to any of these angles over and over and over and get another point that represents it too. There's just an infinite amount on there. All right, now, this is why I used tangent on there instead of sine or cosine on our angle, because that's actually the conversion for it. If you don't want to have to draw the triangle every single time, but we know that what's x squared on this picture right here, what is x squared plus y squared always going to be? R squared, yeah. So put that in your notes. That's r squared always. And tangent is always what over what on our picture here? But on the picture, yeah, y over x. It is sine over cosine, but on the picture it's y over x. Okay, which trig function would you use to find x if you don't want to use the y? You want to use just the x and the r. Which trig function would you use with theta here? Yeah, cosine, right? Cosine is adjacent over hypotenuse. So you could say that the cosine of theta is equal to the adjacent side over the hypotenuse. So if I solve that for x, I just get the r over here, and x is equal to the cosine, r times the cosine of theta. Okay, which function would you use to find y? If you don't want to use the x, you just want the y and the r. Yeah, so the sine of the angle is equal to y over r. And again, you multiply both sides by r, and it's off there. So y is equal to the r times the sine of theta. Yeah. Anyway, so we use SOHCAHTOA, Pythagorean's theorem, all those kind of things to come up with these. These are equations, they're called conversion equations, and they're going to help you convert back and forth. Just like on our first one, we actually drew a right triangle. We did Pythagorean's theorem. We did the tangent of the angle. We did these kind of things. These things help you convert back and forth between points and equations. Okay, so you're going to use these a lot. All right, so here they are again. Another form of this is if you want to think of r as actually the, obviously if r squared is x squared plus y squared, then you could square root both sides. You do have a plus or minus on there, and so you want to think, I always use the positive. I think if you get to choose the radius, you might as well choose the positive one because it's easier to think about it. And then when you're doing finding the angle, true it is the y over the x, but you also have to think what quadrant are you in? Because you have two quadrants where tangent is positive and two quadrants where tangent is negative. Remember, your tangent is positive here, negative, positive, and negative, because we do a negative over negative down there in the third quadrant makes positive. So you have to think about what quadrant the point that you're dealing with is. So if I gave you some point over here in this quadrant like we just had, you know that you're not going to pick the tangent thing that's over in this quadrant over here, even though that you would get a negative in both of those. Both of those, the tangent is negative. You would want the one in this quadrant. So it's important for you to look at where's the point at first, what quadrant, and then from there you can do tangent of the angle is equal to y over x and come up with the correct angle. Okay, just like we did on the first ones. Okay, so if we are we're going to just change a few points here just to practice. So change the point 2 and pi to rectangular form. So there's a couple ways to do this. What's one way to do this? What do you think?
2 equal r cosine theta.
Okay, 2 equals r cosine theta. Well, actually, isn't 2 the r? 2 is the r. So that formula is right here that x is equal to that. So we actually want the x over here. X is equal to the r, which is 2, times the cosine of theta, times the cosine of pi. Well, what's the cosine of pi? It's what? -1. So this is actually -2. Okay, and then the y coordinate is r times the sine of theta. So put your 2 in and then sine of pi. What's sine of pi? What is it? 0. So this is the point -2, 0. Okay. Now, if it's a lot of times when the angle they gave you is something that's on an axis, like isn't that on the axis? It's just right here. So you went this direction and you went 2 units in that direction. So you went to the point -2, 0. If it's on an axis, you don't have to use the conversion things. You can just think about it and go, oh, okay, well, it's -2, 0. It's pretty easy to think about. But when it's not on an axis, I would use the conversion things. It's a lot easier, like this one. Okay, I know that is, you got -3, 3. I'm going to have one of the fourths, right? That's going to be splitting one of the quadrants right in half. So it's going to be a pi fourth somewhere is my reference angle. But it's in the second quadrant, so I'm thinking it's probably 3 pi fourths. So, but let's just use our formulas here. X is equal to the r, which is this, oh wait, we're going the other direction here now. Sorry. We're going to polar. So we want to use actually these formulas down here when we're doing this. So we actually have to come up with an r and a theta this time instead of an x and y. You notice on the other one, on problem 3, I was coming up with rectangular, so I started with, well, that means x has to equal something and y has to equal something. So on the other one, we want to start with our r and our theta because that's what we're trying to find. So I'm going to start with the r is equal to the square root of, using this one right here. You can do the r squared if you want to. X squared plus y squared. And simplify that. What is that? Yeah, square root of 18, which is, what's that simplify to?
3 squared 2.
Right, 3 square root of 2. So that's r. And then I need theta. So I'll use my other formula here. The tangent of theta is going to be y over x, which was 3 over negative 3, or where is the tangent of theta equal to negative 1? And remember, again, we got to think about what quadrant we're in. So we're in the second quadrant here. We go over negative 3 and up positive 3 there. So we know that that is at 3 pi fourths, that angle. Okay, you got to know your angles, super important. So our point then, don't forget it's the r that goes first, so it's 3 square root of 2 comma 3 pi fourths. Okay. Or it's negative 3 square root of 2 comma 7 pi fourths. But who wants to get complicated? Let's just leave it like this. Give the simplest answer. You might, don't tax your brain. All right, so let me see, before we move on to equations, let me see, 5 to 0, can you do the point conversion back and forth? Awesome. Isis, I didn't see you there. You okay? All right. Okay, let's go to conversions of equations. We're using this same exact conversion thing, so same formulas here to convert, and we've got them written down here. So to convert rectangular equations to polar, you just use the same things. We know what x is, we know what y is there, and we have this equation here. Okay, you're not using the tangent as equal tangent of theta because you're trying to convert two thetas, and these, when you use these two formulas up here, you'll get theta in the equation. So you don't need the tangent of theta is equal to y over x, just these three. So just some clues. These are the ones that's like, okay, how the heck do I do this? Can you see, if you're trying to convert to polar, you want to get the r and the theta in there, and you want the x and the y out. So you got to find something to substitute for that y. Can you see something you can substitute? What? R sine of theta. So just put r sine of theta equals 4. And I now have an equation that's polar now instead of parametric because it's got an r and a theta instead of x's and y's. However, polar equations always have r equals. Just like we have when we do our x and y equations, we always do y equals, and that's what we put in calculators. So I had you change your calculator to polar mode. I want you to go into that right now. We're going to actually solve this for r, and then we're going to put it in the calculator. So divide both sides by sine of theta. And r then is equal to 4 divided by sine of theta. So if you're in polar mode and you have it's in radians in your calculator, go in there and you'll notice now instead of y's, there's r's. And type that in there, 4 divided by sine of theta. When you hit the variable key, normally the x key, now it'll have a theta there as you do it. Okay, and graph it. What's it look like? Yeah, there is no polar coordinate thing on there. It still looks like a rectangular, but you got to envision that there's all of these invisible circles that are on there. It actually looks like this straight line here. That's because it was y equals 4, right? So this is basically y equals 4 in polar equation. Now, to me, it's a lot easier in rectangular, right? Some of them in polar equation, it's like, ugh, why would you do that? So this one isn't very convenient, really. Some other ones, though, it's really convenient to have them in polar instead. Once you get really complicated, then polar can be much more simple to do than rectangular. But this one, isn't this just a line? This is y equals 3x plus 2. So again, in rectangular, that's pretty basic, right? It's just a line, y-intercept of 2, slope of 3. But let's see what it is in polar. So what can you substitute? Remember, we're trying to get the x and the y gone and r and theta in there instead. So what can I put in? What can I substitute in for this x?
R cosine.
Yeah, r cosine of theta. So 3 times r cosine of theta. And then, of course, again, for the y, we can plug in our r sine of theta. So minus r sine of theta plus 2 equals 0. So that is a polar equation, but we can't put it in our calculator because it's not solved for r. So we always solve for r. So we'll move our 2 over to the other side. And this part here, I've got to get r. I'm trying to get r alone, right? So I'm going to subtract that 2 to the other side and then just factor an r out. 3 cosine of theta minus sine of theta is equal to negative 2. Okay, and then you can just divide that, what's in that parenthesis, off. So put this in your calculator. Make sure you get the whole denominator in a parenthesis. And it probably puts more parentheses in here all over. You got tons of parentheses now going on. You got all these parentheses. Okay. By the way, if you over here on the first one on number 5, we didn't really need a parenthesis on it, but I would get in the habit of putting the entire denominator and the entire numerator, especially if there's things added, in parentheses. But the denominator, even if things are just multiplied, put them. That's what screws people up. They'll have like 3 divided by 2 pi, and if you put that in your calculator like that, it doesn't divide by the pi. You got to get a parenthesis around that. So just be careful. You guys are pretty good at your calculators, so, but just in case. Okay, so when you drew this one on there, it should have come out to look like this line. It's got a intercept of 2, a slope of 3. It looks something like that. But look how complicated it was in polar. So again, this is another one that it's much better to have it in rectangular on here. All right. But let's look at our next one here. So this one, there's a couple ways you could do it. So if you were just thinking about what we've been doing, couldn't you just put in for every x and y, you could just put in r cosine of theta and r sine of theta. So we could do it that way. We could put in here r cosine of theta squared plus r sine of theta squared minus, out of room, move over, minus 2 times r cosine of theta equals 0. Okay? So look at these right here, first of all. Don't they both have an r squared in it? So, and I know that one's got a cosine and then plus the sine squared, cosine squared plus sine squared. What is cosine squared plus sine squared? It's 1. So I know that if I factor out an r squared out of that, I'll have a cosine squared plus sine squared multiplied by the r squared, which is just 1. So this equation here now just becomes r squared minus 2r cosine of theta equals 0. But can anybody see a shorter way to get directly to this instead of doing what we did? What did we do? What can we do? Go ahead.
Okay, what I did is I just moved the negative 2x over to on the other side of the equation.
Uh-huh.
And then the x squared plus y squared, I just changed to r squared.
Exactly. If you ever see x squared plus y squared, just replace it with r squared. So you don't have to go through all that stuff. We could have gotten directly to this step by just putting in the r squared there for it. Now we've got r's in both of these terms. So if you did move that 2r cosine of theta to the other side, you'd want to get them on the same side. Why do we have to get these on the same side? Yeah, we have to factor. So when you're solving things and you have it set equal to 0, you factor it. So we're going to take an r out, and then we have r minus 2 cosine of theta equals 0. And whenever two factors are multiplied and they equal 0, then you can set each one of them equal to 0. So either r equals 0 or r minus 2 cosine of theta equals 0. Okay, don't get the 2r cosine of theta on the right side and then divide by r. Because if you do that, you can lose one of your answers. Like you wouldn't have this r equals 0. In this particular case, the r equals 0 is kind of redundant. I'll show you why in a second. But this one we could solve for r. So r equals 2 cosine of theta. And that's my equation there. So I want you to put that in your calculator. Put in r equals 2 cosine of theta. And in your polar mode there. And let's see what it looks like. Okay, after you put it in, you might want to hit zoom square because it will distort the shape on you. It probably looks like an oval, right? But when you hit zoom square, what's it look like? It's actually a circle, yeah. This is a circle, and can you see, where does this 2 come into play on our circle? What is that? Can you see it? Yeah, it's the diameter. So the radius of this is 1. And it's off on you'll notice that as we do these cosine graphs on here, they always are like sitting right on that axis, on the x-axis like that splits it right in half. And this one is to the right. What do you think would happen if you put in, say, r equals negative 2 cosine of theta? My pen is not working all of a sudden. Cosine of theta, yeah. Try that. What's it do? This one over here looked like this. There was 2 there. Circle with radius 1, centered at 1, 0. What's it, if you put a negative, where's it go? Yeah, it goes on the other side over here. It's now centered. It's still a circle of radius 1, centered at negative 1, 0 now. It's still got diameter 2. So the positive cosines are going to be on the right side of the axis. The negative cosines are going to be on the left side of the axis. So what do you think would happen if you change it to sine? Where would it move? Where?
To the middle.
Try it. Put it in and see. Change it to 2 cosine. Don't put negative, just put 2 cosine of theta. Where did it go? To the y-axis, yeah. So you'll notice that the signs, at least for circles, the signs are going to be, moves it up symmetrical over the y-axis. So 2 sine of theta is up here. What would happen then if I make it negative, even without graphing it? Tell me in your calculator, what's it going to do? Yeah, it's going to move it down here. Okay. Now, if we had done up on this thing here, that equation, if we had taken that and gathered our x's together, oh my gosh, my pen's having a heart attack today. And we completed the square here, so I take half of negative 2 is negative 1, square that, I get positive 1. Add 1 to both sides here then this factors to x minus 1 squared plus y squared equals 1. That's a circle centered at the point 1, 0, because that's what's subtracted from each one of the coordinates, and it's got a radius of 1. That was our first one that we did, which was right here. So it's centered at 1, 0, radius of 1. So you could have gotten it from that, but this one, I think it's pretty elegant the way that you can draw a circle on an axis here. Now, if you want to move the circle off the axis, it gets way more complicated on polar. But a circle on a polar axis like this, you know, these are pretty simple here. All right. Whoops, that didn't work. Let me group this. See if it'll move. Yep, okay. Okay, so going to polar from rectangular, I think is super easy because you either take the x's and y's and put in r cosine of theta or r sine of theta, and if you see an x squared plus y squared, you put in the r squared. That's pretty basic, right? Go in the other direction. You have to think a little bit more out of the box a little bit. So to convert polar equations to rectangular, you use the same substitutions, but it's a little bit trickier. If you can get an r squared to show up, so it might not be in there already. In fact, most of the time it's not. But if you can get this r squared to show up somehow in a polar equation, then you can replace it with an x squared plus y squared. But look at our equations. I don't see any r squareds down there in 8, 9, and 10, right? So to get that, a lot of times you could either square the side, like if you've got an r or a negative r on a side, you could square it. Or you could multiply both sides by an r. Those are the two tips I want you to keep in mind. Squaring a side or multiplying it by r. If you try one and it doesn't give you something nice, try the other. Try multiplying by r. So you want to use those tricks on there. And again, you're looking to get an r squared to show up so that you can substitute it out with an x squared plus y squared. Or you're looking for an r cosine of theta or an r sine of theta that you can take out and put in the x or the y back in. Okay, so we're working backwards here. So what do you think on number 8 that we should do?
Square it.
Yeah, square both sides, because you just got an r there. So this would be r squared is equal to negative 2 times negative 2 is positive 4. Okay, so now I can just plug in my x squared plus y squared for the r squared, and I'm done. So that was a circle centered at the origin with what radius? Yeah, 2, the square root of 4. So the radius here is 2. Well, look at my equation. Whenever you just have r equals a number, that means on the polar coordinates, why is this being so weird? I would just go out to the radius of 2, and it doesn't matter which direction. If I go out negative 2 like this, if I go to negative 2 right here, and then I draw my circle, that's a really bad circle. I can't draw a circle today, but anyway, you can see, so this is the same equation if I had started with r equals positive 2, right? Doesn't matter, negative 2, positive 2. It doesn't matter. You're just going out anywhere on this circle. You don't even have an angle. You can go anywhere you want and just go out a radius of 2 and you hit that circle, okay? All right, let's try number 9. Let's see, the right side is pretty close to what we want. We want an r in there, though. So what can we do on both sides of this? Right, multiply both sides by r. So this will be r squared is equal to 3r cosine of theta. Now I can see right away, I can take this r cosine of theta out and put in x. And what can I put in for r squared? Right, x squared plus y squared. And you're done. You can, like you said, if you wanted to get this in the right form, I could subtract the 3x to the left side, and like I did on the problem, what was it, problem number 7, I think, I could actually complete the square and come up with it in the nice form that we want, but this is totally fine. You can just leave it like that. You can move it all on one side, whatever. Okay, what about the next one? 2 cosecant of theta. Remember, you're trying to get r sine of theta, r cosine of theta, or r squared to show up. So what do you think you could do?
Multiply each side by sine theta.
Multiply each side by sine theta? Close. We want a sine theta, but can you see, how does cosecant relate to sine?
It's 1 over sine.
It's 1 over sine, right? So couldn't I just replace the r with 1 over sine of theta? So it'll be 2 over sine of theta. Now, how do you get rid of this fraction?
Multiply the sine theta on both sides.
Right, multiply sine theta on both sides, and then now I've got it. There's my r sine of theta. I can replace it with a y. So this is just y equals 2. Okay? All right, let me see 5 to 0. Can you convert the equations back and forth? We haven't even gotten to calculus yet. I see where you're at. Okay. All right. Okay, I just wanted to show you this. This is like what we were saying, the circle. Here's a circle of radius 2. In polar, circle is so much less complicated if it's centered at the origin. Because all you got to do is just say what you want the radius to be. If you want a line that goes through the origin, again, it's super easy to do on polar. If it's not going through the origin, we saw the ones we did before, they got way more complicated. But any that are going through the origin, you just say what you want the angle to be. And you don't even have to say a radius because you're just saying, I just want to draw a line at this angle. That's it. Okay? So if you're going through the pole with the straight line, radial angles are super easy. If you're doing a circle centered at the origin, radial equations there are super easy for that too. All right. But like we said, the other ones can get way more complicated. Now this is where it gets really cool. Okay, so we are supposed to graph these on our calculator. And it has some that we're doing on our calculator and others that we're actually going to like make a chart for because it would take too long if we did them all making charts for them. So first thing I want you to do, before you even think about it, before you type it in your calculator rather, I want you to think about it. And we just did ones like this. Where's this going to end up? Do you remember? On the x-axis, and it's a positive 2, so which side of the y-axis is it going to be on? The right side, yeah. So it'll be over here, and it's got a diameter of 2. So it'll go through like this, right? You can put it in your calculator if you want, but it goes through at 2 there. It's got a maximum height up here of 1, maximum at the bottom would be -1, and that center point is the point 1, 0. So really the center is not on the graph. So technically, I shouldn't have that point on there. That's just to help you kind of get an idea where the center is, but the center is actually not part of the graph. Now before, when we were back on problem number 7, so look back at problem 7. This was our answer to problem 7. We had r equals 2 cosine of theta, and then we also had r equals 0. Can you see now why I said that the r equals 0 is redundant? What does r equals 0 mean? There's no radius. So if there's no radius and you're starting at the pole, that's just the point 0, 0 in rectangular. Well, it's already on our graph right there. So that's why,
No, that's R.
that is why we don't need this when we were doing that particular problem. Okay? All right, so let's go to the next one. And on this one, we know where this is going to end up, right? But we're going to try to relate this to points on this one because we're going to need it for some other ones. So where's it going to end up? It's a positive and it's a sine of theta. Where's it going to go?
Like on 2 pi, like on that y.
Yeah, on the, is it going to be above or below the x-axis?
Above.
Above, yeah, and it's going to be right on that y-axis. So it's going to end up like this, right up here. And this radius here, or the diameter there, is 5. Okay, but if we didn't know that, and we were going to graph this, we're going to have thetas and r's. Now remember, it's easier if you actually are plugging in the thetas. So if you just start on the unit circle, and I just plug in the main points, like plug in 0 on there. If you plug in 0 and you do 5, you're just plugging them into this equation up here. If I do 5 sine of 0, I'm going to get 0 for r. So that's this first point right there. So this is starting right there. Right at that, at 0, 0. And then if I plug in, say, how about pi 6th? What is the sine of pi 6th? Pi 6th, right there. What's that sine? 1/2, yeah. So it's 1/2 times 5, or 5/2. So this is pi 6th and 5/2 would be, I'd go out pi 6th, like that angle at pi 6, and then go out 5/2, about 2.5, gets me right there. So I've got another point on the graph. Then let's just go pi halves maybe. What's the sine of pi halves?
1.
It's 1. So we have a 5 there. So that gives me the point straight up. So you can see the direction that it's drawing here. It's starting here, it's going out to the right and drawing up to the top. And then let's do pi. We don't need to get really particular here. What's sine of pi? It's zeros, right? So that's going to be this other part. We could graph a whole bunch of other points in the middle there, but we don't really need, it's just all the points that are on the other part of the circle. And then it ends back down here. So this one, to draw these circles on here, you only need the angles from 0 to pi to draw them. When you put this in your calculator, if you go into window, you can see sometimes it'll go like, it usually does 0 to 2 pi on the window, on the highest value of theta and the lowest value of theta. But it really only needs 0 to pi to draw this on there. The second time around is just tracing the same circle again. Okay, so now let's go on to some other ones. Those are circles. Are you guys all, how do we feel about circles? Let me see, 5 to 0, can you do these circles that are on the x or y axis? Okay. Okay, let's go to the rose petals then. So can you see how these next equations are different? What did we change?
Cosine something multiplied by theta.
Right, you've got something in there multiplied by the theta. So these are the really cool ones. So go ahead and graph that and see what it looks like. See why they call it rose petals? They should actually call it something else because it doesn't really look like a rose, but petals, I guess, of a flower. Should call it daisy or something. It looks like a daisy. Can you see what's it look like? How many petals does it have? 4. Did you watch where it started drawing? If you watched it draw, it actually starts out here on the right side because we're doing a cosine petal, so it's going to start on that x-axis. If it's a sine petal, it usually starts right in the origin on there. Okay, so, because think about your sine and cosine graph, your regular sine and cosine. Doesn't cosine start at 0, 0? And so if you're doing the rose petal of sine, it starts at 0, 0 also, whereas cosine starts out on the axes. But it doesn't really matter. I mean, you can just sketch it here. I don't know why my pen is not working very good here today. But it looks something like this, right? So go back into it. If yours won't do it, sometimes mine I have to change the equation. So just put like a +0 or something on the end so it thinks you changed it, and watch it graph it. Watch how it does it. It doesn't draw it like I drew it. It's one continuous line. Can you see where it's going? Starts out here on the right. Does it start going up or down? Yeah, it starts up and it just makes a continuous line. It goes like this. Goes around, goes around, goes around, and it ends right there. Okay. Kind of cool. So for the rose petals here, you have a 2 inside there, and how many petals did you end up with? 4. So whenever this is an even number in here, it doubles the number of petals that you have. Okay, and if it's a cosine, it's going to be, see how this one is straddling the x-axis again? It looks like it's cutting that petal's right, being cut by the x-axis in half there. It'll do the same thing on even ones on there. Okay, what else did I want to tell you about that one? Oh, this one, if you look at the different angles and stuff, you actually did use all of the values of the angles from 0 to 2 pi. If you only did from 0 to pi on that, if you went into window and changed, just go from 0 to pi, it would only draw half of it. Okay, and it would stop. Okay, the next one, try this one. Actually, before we move off of this one, let's do this same thing here that we did, but let's change it to a sine and see what it does. Change it to sine. So make it r equals, you don't have to write this down or anything, I just want you to get used to playing with these. R equals 3 sine of 2 theta. It's still going to have 4 petals because it's got an even number in there, but where did the petals move to? Yeah, they just shifted. Because isn't that what the sine and cosine graph is? You just take the sine graph, you shift it over, you'll get the cosine graph. It shifts it. So it becomes like this. And it starts in the middle and then starts going around. It makes a continuous curve. It starts right there at 0, 0, and it does that continuous thing again. This one, interestingly, though, it again needs the 0 to 2 pi to get that one. Anytime you have an even number in there, you got to have all of the angles to get the whole thing. So go ahead and do the next one here. R equals 4 sine of 3. Now this one is an odd number. How many petals do you get when you draw this one? What'd you get? 3 petals. So when it's an odd number in there with the theta, then whatever that number is, that's how many petals you're going to get. Now, you notice that the number in front of these is different. On part A, we had a 3. On part B here, on number 12, we have a 4. That's going to be your length of your petal, basically. So this one, you notice that it's a sine function. So it actually starts in the middle, and it makes a loop, and then it makes another loop, and then it makes the last loop up there in the other quadrant. See how it's symmetrical over the y-axis like this? Symmetrical over the y. Sorry, my last loop got kind of weird there. Okay, symmetrical over y. And if you looked at the distance, like if you had those circles on here, those radial circles, you'd see that this out here on the edge of each one of these is the 4th circle. It's a radius of 4. That distance out there is 4. 1, 2, 3, 4. 4 circles out. Okay, on this one, they wanted us to do a chart on here. If we did, we did it on the calculator, but if we were doing it with r's and thetas, if we start with 0, sine of 0 is 0, so that gets us starting right in the middle again. Pardon me. If we plug in pi 6th, we actually get sine of 3 pi 6th, which is sine of a half, or sine of not a half, sine of pi halves. What's sine of pi halves? Yeah, 1, and then times 4 gives us 4. So that gives us this point out here. So it went around here, and it looped onto that spot there. Then you keep doing all of them around there. You put in, say, pi thirds, and you end up then sine of pi, which is 0. We get back to our 0, so it gets us back here. And then you can keep going. You only need to get points out to pi here. If you keep going there, you'll notice that, we could do a whole bunch there, but we don't really need to. Pardon me, a frog in my throat today. You only need the values from 0 to pi for theta on this to get the complete 3 petals. Okay, so the only time you're going to need the whole thing from 0 to 2 pi is if you have this where you have the even number of petals, because basically you got to go around twice kind of thing on there. All right. Okay, well, let's do one more on there. What would happen if you change this last one here then to cosine? So do, just in your calculator, r equals 3 cosine of 3 theta, or 4 cosine of 3 theta, sorry. So what's it look like? It's still got 3 petals, but where did the petals move?
Now the petal that's on the axis is on the x-axis.
Right, exactly, because remember when we do these with x or with cosine, it's got to straddle the x. So it's going to be the same thing, it's just shifted around a little. Looks like that. It actually starts out here on the end because cosine doesn't start in the middle. And it goes like this. It goes around, makes this loop, and then that loop, and that loop. And again, you only need it from 0 to pi. The angles from 0 to pi would get that. But it doesn't really matter. If you have more angles on there, it'll just loop it around. Just keep looping. Okay? Keep tracing over the same thing. All right, let me see, 5 to 0, can you do the rose petals? Do you understand how they are? I know this is new, all kind of freaky, but you can make some pretty fun pictures on your calculator now. Okay, now we're going to move to limicons. The C with the little weird thing underneath it, I don't know what you call that. It's pronounced like an X, S, so it's limicon. So now you can see we're adding something to the cosine or the sine on there. So go ahead and do part A there. R equals 2 minus 3 cosine of theta. What's it look like? Do you notice where it starts? It starts drawing like right here. And it goes around like this. Whoop. Ends right there. Okay. They actually call these, let's see, well, they're called limicons. I think it's the next one that's just called a cardioid there. I can't remember. We'll have to look and see. Okay, so you notice on this one that you had this little loop that showed up in there. Again, see how it's straddling the x-axis because it's a cosine one on there. A sine one, where do you think it's going to straddle? Y-axis, yeah. So well, we're going to actually make a chart for part B here because it doesn't have it in bolded, so we're supposed to make a r theta chart. So we'll start by plugging in 0 for sine right there. So we get just 3 plus 0. And then let's plug in, how about pi sixth? What was sine of pi sixth?
1/2.
A half. So a half times 3 is 3 halves. Plus 3 is 9 halves, or 4.5. Okay, and then let's put in, I put in the nice number so I don't have like square root of 3 on whatever, so, or square root of 2. So if we put in pi halves, sine of pi halves is 1, so we get 3 plus 3, or 6. So let's graph those points, see where we're going here. So we started at 0, 3. So that's over, or 3, 0 rather, that's over here. The angle of 0, the radius of 3. And then we go up to the angle of pi sixth, and we do 4.5. So it's probably somewhere up here, like that. I'm just kind of guessing. Might be a little bit more out. And then at pi halves, we're up to 6. I think I better make these smaller. I'm off my chart already here. Because 1, 2, 3, 4, 5, 6. I got to get up to 6 there, so I'll make these a little bit smaller. So something like that. So it's starting like this, going like that. Okay, and then it's just going to do the exact same thing. We could put more points on there. In fact, let's put on there pi. Sine of pi is 0, so we're back to 3. So it comes over 1, 2, 3. It makes that same shape on the other side, comes down here to here. Oh, yeah, so it's radius of 3. You got to remember, even though that rectangular point is the point -3, 0, on polar, that's this. I go the pi direction 3, okay? All right, and then let's keep going. Let's just put in the poles and see where it goes here. So let's put in, or excuse me, the axes of the unit circle. So 3 pi, not the pole, what was I thinking? 3 pi halves, the sine of 3 pi halves is what? -1, yeah, so it'll be 3 minus 3 there, which is 0. So this, it loops up here, and then it comes in, and it actually makes a little point right there. And then if you go back to 2 pi, then you're back to 3. So it comes back out and makes the other. So this one they call a cardioid because it looks kind of like a heart on there. Okay.
This is a good.
All right, and this one we say it has an inner loop. This one is a cardioid. The pen will not write. I don't know what's wrong with it today. Sorry, that's supposed to say cardioid. You can't really read it very well, but all right. They also have ones that are kind of dimpled, like instead of coming all the way in, it comes in and just kind of goes like this and out, like that. So it has to do with the relationship of these numbers here. If this number in the front there is smaller than the number in front of the cosine, it will make the loop, okay? If the numbers are the same, it makes the cardioid. And we're talking absolute value of these numbers here. If the number that is over here on the first is bigger, then it makes either a dimpled like this, or it gets really flat and starts looking like a circle, the bigger the number gets. I'll show you that in a minute. But that same thing to do with the negative and positive. Look at our signs here. So up here on this first one, I have a negative, come on, pen. I have a negative right there. And see how it's over here on the negative part of the x-axis? If that had been a positive 2 plus 3 cosine, it would have been drawn over on this side. See how it's a positive sign, so it's up above? If it had been a negative 3 there, negative 3 sign would be below. It would be down here, being drawn the other direction. My pen does not want to write today. Okay, the last one, those are limicons. The last one is called a lemniscate. And that one, well, go ahead and put it in your calculator. You can see what it looks like. Lemniscate looks like a figure 8. Lemniscate, figure 8. Okay. And the radius of this, if you took whatever is in front of the sign there and you do the square root of it, that's how, what the radius of one of those petals is out there. All right. If you solve this for r, you would get r is equal to plus or minus square root of 9 sine of 2 theta. This would be the plus and the minus. It's two separate equations, and you could just draw just one of them, and it would give you the same picture. The only difference is one of them draws at one direction and the other one draws at the opposite direction, but they give you the same thing there on this one, the same shape. All right, so I have this little thing here. I don't know if you want to take a picture of this, if it would help, or you can get it from the video later if you want to look at it. It's not in the filled-in notes online, though. So this is kind of a summary of all of the cardioid ones, the, what are they called, limicons. So you have the limicon with an inner loop, and that's when the number in the front is smaller than the number in front of the sign. Okay, the number you're adding is smaller. And by the way, it says you've got two equations up here, the r is sine and r is cosine, but what are all my pictures of? Are they the sines or the cosines?
Cosine.
They're all the cosines, yeah, so they're all the cosine one. But it's the same principle with the sine one. And then this one, you know, where they equal 1 there, that's where the A and the B are equal to each other. That's a cardioid or a heart-shaped. And then you've got a dimpled, so anytime this number out in the front, the A is bigger than B, if it's not a lot bigger, if it's somewhere when you put A over B, if it's still less than 2, then it just makes a little dimple like this. If it starts getting 2 or greater, it starts getting flatter and flatter like this, and the greater that number gets, the more it starts looking like a circle. Okay? All right. So that's our first part here. And then this is a summary of the rose petals on here, where you've got odd number and even number and where are they centered and, you know, sine or cosine kind of thing on there. So if you want to take a picture of that one. Remember, if it's got an even number in there, it doubles the number of petals. So hopefully, if you just, after you're doing your homework today, I'm hoping that you'd get used to, if you see, you know, r equals 2 sine of theta or whatever, you know what it looks like. Just like you know what y equals x squared looks like, okay? So hopefully they'll become a little bit more familiar with you here. And then this is our last one that has the circles and the lemniscates on it. We didn't do the lemniscate of the cosine, but all it does is just shift it around so that it becomes symmetrical over the x-axis again. It's weird because you would think the lemniscate with sine would be right on the y-axis, but it's not. It's off. It's shifted just a little bit, not entirely 90 degrees. Okay? All right. So that said, this is the summary he has in your book. I like the picture summary a little better, but this is basically saying the same thing. All right. You notice that all the Ones with cosine always had x-axis symmetry, and all the ones with sine always had y-axis symmetry. Even if they're not centered right on the axis, they always have that symmetry where you have the mirror image over the x or mirror image over the y. So we've gotten through all that stuff. Now we need to get to the calculus part of it. It took us that long to get all that stuff. That's what we used to teach in pre-calc. Okay, so what if they ask you to find the slope of a tangent line? Okay, be really careful, because if you're given, let's say I give you some equation that is like r is equal to 3 plus 2 cosine of theta. It's definitely Friday. My pen does not want to write today. Oh, the tip wasn't screwed on tight. I wonder if that was it. Oh, the tip wasn't on tight. Finally figured it out. Okay. Anyway, so let's say I give you this, and they say find dr d theta. Don't you just do the derivative? Because it's with respect to theta. You want the derivative of r, so you want dr d theta with respect to theta, so you just do derivative of 3 is 0. Derivative of 2 cosine of theta is negative 2 sine of theta, and you'd be done, right? And maybe they'd give you a r theta point, and you could plug it in and even find values or whatever, you know, maybe a value of theta that they want you to do this at. You could do all that kind of stuff. However, they don't do that very often, but be careful. Don't assume that because you have a polar equation that it's going to be this. You got to read the instructions. So most of the time when they give you stuff with polars like this, it's not this dr d theta unless they specifically say that. They want you usually to find like the slope of a tangent line. The slope of a tangent line is much, much easier to do in rectangular than it is in polar. So a lot of people are like, well, let's just change everything to rectangular then, and we can do it from there. Well, kinda, but there's actually a shorter method of doing it, and sometimes it's definitely shorter. All you do is you think about, if you have some equation, so you have like that one that I had, maybe r is equal to, or I don't even know what I had, 3 plus 2 cosine theta, is that what I had? God, that's so much better. I should have noticed that I was not writing before. Okay, so I have this equation here, and I just know that, remember that x is r cosine of theta. Well, this is r, right? So I could change this to x is equal to r times the cosine of theta. Okay? Now I have an x for this. And then I can do the same thing for y. I can say, well, I know that y is just r times sine of theta. So I'll say y is equal to this r again times the sine of theta. Now I have an x and a y. So now we go back and think about parametric. Remember parametric, you have an equation for x, you have an equation for y, and each of them have a parameter in it. The parameter this time is the theta. So we treat it just like it's a parametric now, and all we have to do to find dy dx is to just do dy d theta and dx d theta, so we just do the derivative of each one of these and put one over the other, and we'll have the formula for dy dx. And that formula for dy dx is now a formula for a rectangular equation, although we do have to change our theta so we can figure out what the rectangular point we're going to plug in is. But still, we're just going to use parametric. We're going to change it to the x and the y. So every time if they say find the slope of the tangent line, then every time you're going to just think, okay, I'm just going to take whatever r is, and I'm going to make x equal to that times the cosine of theta and y equal to that times the sine of theta, and I'm going to go to parametric. Okay, and I'm going to do my slope just like I did in the parametric section. Okay, so let's do one. So it says again, find the equation. This one says the whole equation. So let's first just start with, let's find the slope of the tangent line. Okay, because to do an equation, we have to have the point and the slope, right? They gave us a point, and nicely, this point and this equation are in polar form, and our equation that we're going to end up with is always in rectangular. Because remember how complicated the equations were if they're not on a pole in polar? They were ugly. So we want to do equations always of tangent lines in rectangular. So we're starting with this polar information and moving to rectangular. However, it's really nice that they gave us a point here, 2, 0. Think about that. In polar form, that's the rate, the angle of 0 and over 2. Isn't that just the point 2, 0 in rectangular also? So in this particular case, because they gave it to us on the 0 axis there, the 0 angle on the x-axis, it turns out to be the exact same point in rectangular. So that's in polar form, so rectangular it's the same for this point. That's not always the case, it's just for this particular point it was the same. So you always want to get the point that they gave you, you want to get it in rectangular so that you can plug it into your point and slope form for the equation of the line. So let's go to do our slope then. So we want dy dx, so we're going to start with what is x. So here's r. R is, we'll come back, there we go. R is 2 times 1 minus sine of theta times, is it cosine or sine for x?
Cosine.
Yep, cosine of theta. Okay, and then what y is equal to, I think I said r back there when I was doing, I meant x. X is equal to that, and then y is equal to the same thing, r, the same r, but this time times what? Sine of theta. Okay? So now to get our slope, we've got to do the derivative of each of these and then just put the dy d theta over the dx d theta. So dx d theta, we're going to have to use what formula for this?
Product rule.
Product rule, yeah, we got to use product rule. In fact, if you want to make it, if you want to distribute a 2 into one of them, I'm going to make it 2 times the cosine of theta times 1 minus sine of theta, just so that it's a little easier for me to see. So here's my 2 factors of that product. So we'll do the first, or whichever way, it doesn't matter which one you want to do first, times the derivative of the other one. What's the derivative of negative sine? Negative cosine of theta. Okay, plus the second times the derivative of the first. What's the derivative of 2 cosine of theta? Right, negative 2 sine of theta. Okay, so there's our dx d theta. You don't even have to simplify it if you don't want to. Okay, and then because we're going to be plugging something in for it, so we're plugging in our theta. Theta in this case is 0. So we're going to plug in 0 for that and simplify. Okay, so our dy d theta, though, let's get our formula for that, is the same thing. I'm going to put the 2 over here, so we'll make it 2 times the sine of theta times 1 minus sine of theta. That's what I'm doing my product rule on. So we have the first times the derivative of the second plus the second times the derivative of the first. Come on, there we go. Times the derivative of the first is what? 2 cosine of theta? Okay, so there's our formula. So when I go to write my dy dx now, it's just going to be 2, let's see, the dy d theta one, so 2 sine, well, let's make it negative 2 sine of theta cosine of theta. And then plus 1 minus sine of theta times 2 cosine of theta, all over my dx d theta, which is 2 cosine of theta. Oh, it'd just be negative 2 cosine of theta squared. This one's not too bad. And then plus 1 minus sine of theta times negative 2 sine of theta. Okay. Now we're going to evaluate this at 0. This is why I didn't simplify it, because I don't need to. I mean, I'm just evaluating this when theta equals 0. Plug in a 0 for each one. What's this first term going to go to then? Isn't every term with sine in it going to go to 0? That one's going to go to 0. And then over here I have 1 plus 0, 1 minus 0, times what's 2 cosine of 0? cosine of 0 is 1, so 2 times 1 is 2, over this one is negative 2 times 1, so just negative 2. And this whole term right here, because it's being times by negative 2 sine of theta, is going to be 0. So we ended up with lots of zeros on there. So it was, this is 1 times 2, or just 2 on the top and negative 2 on the bottom. The slope is negative 1. So now I take my point, which happens to be the same point in rectangular, and I take my slope and I write my equation. So the equation is y minus the y coordinate is equal to the slope times x minus the x coordinate. And there's our equation. All right. Okay, so the last question that he has on this one, or the last problem he says is, how would, let me ask you a question first. How would you find points where a polar graph has horizontal or vertical tangents? Because that's what he asked in the last one here. Where do you think? So think of one of these polar graphs, any one that you want, just think of one. Think about, where is it going to have horizontal or vertical tangent lines? What would be true about its slope at horizontal and vertical tangent lines? Right, horizontal tangent lines, the slope equals 0. Or dy dx has to equal 0. And what about vertical? Where it's undefined or doesn't exist. So this is where dy dx is undefined. So remember, that would be where the denominator equals 0. So this is where dx d theta, right? Because this, remember, dy dx is dy d theta over dx d theta. So basically you're looking, where is this dx d theta equal to 0 if you want vertical tangent lines, and where is dy d theta equal to 0 for horizontal tangent lines, okay? That's kind of what we're looking at here. So we have, it says find the points where this has the horizontal tangent lines. And so there's a place for you to draw the graph. I would always suggest that you draw these graphs, because when you're doing these vertical and horizontal, because everybody misses at least one of the places if you don't draw it. But if you draw it and you notice kind of where they're at by looking at it, you won't miss them all. In fact, some of them, they don't even show up in the work. You just have to know by looking at it. So if I draw this, and I have, there's 2's for both the A and the B in my formula here. So it's a rose petal, because I've got to subtract in there. I know it's a rose petal, and, or not a rose petal. It's a cardioid, because I've got to add or subtract there. And this number is the same. And it's a negative here. So I know it's going to be, the most of the cardioid is going to be on the left side of the axis. So it's going to have a point right here at the origin. If you noticed on the cardioid when we drew them, that it's centered on this x-axis. All right, so you notice when we did these that it's centered on that x-axis, but it crosses the y-axis at whatever this number is at the 2. So it's going to look like this. And then if you notice on the other ones, if you double that, that's where it crossed the x-axis. So it looks something like this. That always happens on those cardioids. Okay, so you just go the center like that and up to, it happens even on the inner loops and the outer loops too, that same thing happens. And if it's dimpled, they always have that characteristic where they go up or down, whatever that number is, and then out. Double it. So let's see, where would I have horizontal tangent lines? Yeah, the top and the bottom, right? I should just have 2 when I'm done with this. Does yours have horizontal and vertical on your notes, or just horizontal? Just horizontal. Okay, so there should be 2. So if it's horizontal, we want the top of the dy dx, which is our dy d theta, to be 0. Right? We want this part to be equal to 0. So all we have to do is do dy d theta and set it equal to 0. So I have to get y first. So what do I write for y? Remember what's y? Y is equal to r times which one? Sine of theta, right? So remember, here's r. So what do I write down here? R is equal to, I keep saying r. Y is equal to what?
2 minus 2 cosine theta multiplied by sine.
Right, multiplied by sine of theta. I don't even need to do the dx d theta on this problem, okay? Just the dy d theta. So we have dy d theta is equal to, again, we've got a product rule here, so the first times the derivative of the second plus the second times the derivative of the first, which is 2 sine of theta. Okay, so probably should multiply this out because we actually have to set this equal to 0 now. We want to know when does this equal to 0. So we'll have to do some actual multiplying. So distribute the cosine in there. We get 2 cosine of theta minus 2 cosine squared of theta. And over here I have plus 2 sine squared of theta. So think back about your solving on these kind of things. How do you go about solving this? What would you do? I've got cosines and sines. Got to really dig deep into your trig identities here. Yeah.
You know that sine squared is cosine squared is 1? Could you just look at that?
Sine squared of theta plus cosine squared of theta equals 1. That's true. Do I have a plus here? Problem is that negative. If I wouldn't have had that negative, that would have been awesome, right? But I have a negative. But you're on the right track because we need to get these to all be the same function. They all have to be cosine like that if you can't substitute out right away. So you want to substitute out for this sine squared of theta. You want to substitute something with cosine. Well, if you just subtract cosine squared of theta here on both sides, then you have that sine squared of theta is equal to 1 minus cosine squared of theta. So you're still going to use that Pythagorean identity, but you're going to take this and put it in place of that. So now I have 2 cosine of theta minus 2 cosine squared of theta plus 2 times 1 minus cosine squared of theta. And we'll put it all together here. Let's see, distribute the 2 in there, and we get 2 cosine of theta minus 2 cosine squared of theta plus 2 minus 2 cosine squared of theta. Combining your cosine squared of theta terms together, I'll put them first. We get a negative 4 cosine squared of theta plus 2 cosine of theta plus 2. And remember, that's equal to 0. So what can you do to make this a little bit more simple at this point?
Substitute cosine of x.
Yeah, take out the cosine and put in an x for it. But even before that, I'm thinking I want to, they all have a 2 in it. I'm going to actually factor out a negative 2 because I like to have my cosine, my first term positive. It's just easier, the squared term. So we'll factor out a negative 2. So now it becomes this. Okay. And if it's equal to 0, since that's just a number, I can divide both sides by negative 2. And 0 divided by anything is still that. So I just end up with this. Okay. So now is where, yeah, if you don't like factoring it like this, then go ahead and just substitute out something for the cosine. So like maybe make the cosine of theta equal to x. If you put an x in there, then this becomes an x squared, and that's a minus x. So I have 2x squared minus x minus 1. And then we just, since that's set equal to 0, we can factor it. And that factors just by guess and check pretty quickly. The only way to get 2x squared is a 2x and an x, and the only way to get a 1 is to put a 1 and 1. You just have to figure out which one's negative. And so we want that one negative, so we end up with a negative 2x and a positive 1x. Then you set each one equal to 0. So we'll come over here and do that. So 2x plus 1, but x is really cosine of theta, right? So let's put that back in. 2 cosine of theta plus 1 equals 0, or cosine of theta minus 1 equals 0. So we solve both of those, subtract 1 from both sides, and divide by 2 here, and we get cosine of theta is equal to negative 1/2. Well, where does cosine of theta equal negative 1/2? Think about the unit circle. Where is cosine of theta equal to negative 1/2?
One right next to pi halves, whatever it is.
So what is that one next to pi halves up here? What is it? 2 pi thirds? Where else on the unit circle is it? And 4 pi thirds, yeah. And if you look back at our picture that we drew, look at our picture. See how that is really lining right up with where we want. It's going right to those points where we want it. Okay? Do I think this is going to freak out on me here? Group it all. Okay. All right. So we've got our two theta values there. The other one here, where is cosine? Come on, pen. Cosine of theta equal to 1. Where is cosine equal to 1?
0.
At 0. This is at theta equals 0. But at theta equals 0, look at our picture again there. It's actually right in here, because when we plugged in 0 into our equation, if you plug it back in up there, you get 2 minus 2, or 1. It was this point right there. So theta equals 0, it's where you had a sharp point. Can you have a tangent line at a sharp point? No, there's an infinite number of tangent lines at that sharp point. So even though we got an answer, this is where drawing the graph is really, really helpful, because you need to know that this was not really an answer. So the only value is where it occurs, whereas theta equals 2 pi thirds and 4 pi thirds. Now we're not done, because we actually have to say, we're saying the whole points, and so it's like when we have xy points, we have to plug it back into the original function. So remember, our original function is up here. So we have to plug in r is equal to 2 minus 2 cosine of theta. You want to plug in when theta equals 2 pi thirds. And we get r is equal to 2 minus 2 cosine of 2 pi thirds. And then we're going to also plug it in, and we could do it, I guess, in their notation. I think their notation is actually better. We'll just say r of, you could do it like this, r evaluated at theta equals 2 pi thirds. Is that, or I could say r of, and then my next one would be 4 pi thirds equals 2 minus 2 cosine of 4 pi thirds. I think this one, I like this notation down here a little better. Okay, so you just evaluate both of those, and hang on. Doesn't like it when I move sideways. It doesn't group it together. There you go. Okay, so you just simplify each one of those, and we end up with 2 plus 1 on there? Don't we get 3 on each one of these? Because that's cosine of 2 pi thirds is a half, negative half. And, no, is it just a half? It's a negative half. It's negative, it's 1/2, negative 1/2. And then times negative 2 makes it positive 1. So, yeah, same thing happens on this one. So our points are the point 3, 2 pi thirds and 3, 4 pi thirds. Which, when you look back at the picture, that looks about right. Now, if you were doing this with vertical, chances are you got to make sure that you get all of them. Chances are that you might not get one of them, and the one you don't get sometimes is the one over on the end over there. But just make sure, if you're looking at the picture, you could go, okay, vertically, I should get 1, 2, 3 answers there, okay? So look at your picture, you know how many answers you should get if one of the answers is bogus, if it really is an answer, not like on this one where it wasn't an answer, or doing it the other way. And this one, basically you have one already. You know where that occurs. I mean, that's at the point -4, 0 there. So you could say that one I know is at 4 pi, if you were doing the vertical ones. That one you could already get just by looking at it, and then you'd only have to find the other two on there. And what would you do for that vertical one? What would your process be? Just talking about it. We're not going to do it, but
Where dx d theta does not, or
where
does not
dx d
exist.
theta, but it's where dy d theta doesn't, or dy dx doesn't exist. Though, so that's where dx d theta is equal to 0. So you have to think about that fraction, remember? So you start with dy dx, but that was dy d theta over dx d theta. So you're actually looking, where is dx d theta equal to 0, and that'll be where you have vertical tangent lines, okay? All right, there is another question that he used to have on the homework, or on the lesson. It's not there anymore. It's actually pretty quick, though. If you want to have a tangent line through a pole, let me show you here real quick. It's pretty fast. I'll show you. So let's say you want a tangent line through a pole. Remember, if I have some function like this or whatever, I don't know, maybe it looks like, what would it look like? Something like that. And I want this tangent line right there through that pole or whatever. Then it's just, your answer is just going to be an angle, a radial line, because that's how we write those in. So this is the only time when they ask you to write an equation of a tangent line that you don't change it to rectangular, is if they say do the rectangular or do the tangent line at the pole, because it's super easy to write the equation of a tangent line in polar at a pole. You just write the angle on it. So on this one, all you're doing is you think, if I'm going to write an equation of a tangent line at a pole, this one, let me see, I don't think I have it written on here. You could graph this. What's this one look like?
It has 3 petals, and each petal is 4.
Right, each petal, so it's going to be, and it's symmetrical over, it's going to look something like, each petal is 4, so it's going to look something like this, like that. The sine one, symmetrical over the y-axis. Each one of these is 4, so if I do that circle around at 4, it'd be touching it, supposed to be, like that. Okay, so that's what it looks like. So I'm doing these tangent lines at the pole, so all of these tangent lines here at the pole like that, all of those lines that are tangent on the graph. Well, every one of those lines, if I'm at the pole, what's the radius at the pole? 0. So you're just saying, putting 0 in for r. And then you divide by 4 to just get it, 0 equals sine of 3. Then you just think, well, where is sine 0? Well, sine is, sine of angles are 0. Some other angle, I'll just say some sines of any angle x are 0 when x is equal to 0 and pi and 2 pi and so on, all the way out, and all the negatives, right, of them too. All the multiples of pi. So all I do is I just think, well, then 3 theta is all of these things, 0 and pi and 2 pi and forever in both directions. I guess I could go like that. And then we just divide them all by 3 to get theta. So it'd be 0 and pi thirds and 2 pi thirds forever, like that. And I'll give you all those tangent lines. So actually super fast. But remember, if it doesn't say at the pole, then when you're doing the equations of tangent lines or the slope of the tangent line and you're in polar, you've got to change it to x and y and then do dy d theta over dx d theta and treat it like it's parametric, okay? That was like the longest lesson ever.